the product thing as and the plus thing as or, it's sort of telling you, well, a person is like a string and a maybe gender, and a gender is like, well, a constructor with no fields, or a constructor with no fields, or a constructor which has only one field, which is a string. So we are describing how the data type looks like. Does it make sense?
Yep. If we expand them maybe into like these other constructors the same way, I guess, the other string, it's the same thing, right?
Yeah, you could. So that's actually like a question in many generic libraries, how deep you go. And I will take here the approach which seems to be the most prevalent, which is here when I say a person, I just include maybe gender, but I could also sort of include maybe of the full description of gender, but I only go one level deep. So a thing has like the types of all the fields. And then if you want to look the gender generically, then you need to like sort of do the conversion again to say, okay, now I want you to show me this generically again. But here we are going like just one level deep. So does it make sense? Okay. So so can you try to, like, given this data type, so it's a dog with a name, or a cat which has a color and also a name, or a fish, and all the fish I had in my childhood just lasted for 1 week, so I decided they don't have names; they are just fish. So can you try to come up with a description using these ideas? So fields is a type. You combine things with the fields with a product, and then you offer choice with a plus. And can you come with a description of this?
With the is-like form.
Yeah, with this. Yeah. So I'm right now we are sort of defining. Well, we are keeping it high level. So this is not how it will look like, but these are the main ingredients. And then we will have to define what actually no fields is and one product is and all of that. But yeah, just assume it's a data type that exists. So you don't need to know it to define the generic representation. Okay. Good. So. Well,
string plus open parentheses core times string close parentheses plus no fields.
Yeah. So if you understood this, you've already understood like 50% of all generics things. So because we are going to define how these things work, but at the end of the day, this has been defined in a library. So you don't care. You just care that you can describe your data type. And actually, the cool thing nowadays is that GHC writes this for you. So you don't even need to think. You just write your data type, and because from the data type you can do this, it just writes it for you. So of course, the question now is. So let me open a new file. So. How do we define this plus, this times, these fields and these no fields? So here is where the sort of the tricky part things. We are going to define some functors, and they will look kind of weird. So you have to have a bit of faith with me that this will all work out at the end, because it's not the easiest construction. But okay, so. The only weird thing about this is they are going to be functors. So they are going to have an extra type argument that we are going to have there, and it will keep lying there, and it's really useless at this level of generic programming. Once you go deeper, there is a use for this, but
Module or JSON?
huh? Oh, that's module, yeah. So we said we want to define like a choice, a product, and then these fields and no fields. So the first thing I'm going to define is no fields. So if I want, what's the information about no fields? This is like an empty tuple. So it's like so what I will do is to have like a constructor with no information. There is no information in having no fields. The only information is that there are no fields there. It's like, as I said, like an empty tuple. It's there, but it's useless. So you can also have a field of type T. And I just said that we are going to make it a functor. So just for the sake of it. And this has some information of this type. So this just has some, yeah?
Why is the A for again?
Yeah, it's difficult to explain why it's for. So that's how the generics library does. So the fact that these are functors instead of like normal things make them easy to combine when you want to define generic operations. And this also allows you, because now we are having simple types, which are just like person, which has no type variables. But if you want to define something like list, where you actually have a type variable, this buys you something. So I won't go there. I just want to show the construction. But yeah, it feels, I agree, it feels weird to have this A laying around there. So okay, so if we disregard the A, so if we have a field of type T, the information we have there is just something of type T. So if we have a field of type int, we want an int. So that's why we just have one constructor and it holds an element of type T. And now we have to have these ways to combine things together. So let me call it better C and D. So if we can choose between constructor C and constructor D, that's what the choice says, is, okay, we either chose the one on the left, which is C, so C of A, because these are all functors, or the one on the right. So this is just your either type, but one level up with these things. And in the same way, if we have some field F and some field G on A, well, now this is like a tuple. We want things of the F and things on the G. So we have, I don't know how to say it, but it's like, so this should look a bit as, well, this is like a tuple, but with this weird level type variable A. The sum is like an either, like a choice, and then you have just a way to say no fields and a field of type T. So now we can really, if we have this data type for fish, we can really say the representation of fish is, again, this is going to be something with type A because it's a functor, but it's going to say no fields. No, sorry, it was, I think, string. So that was the name of the dog, or a color, and sorry, I need field now.
Did you mean representation of pet?
Of pet, yeah, definitely. So we have a field of string, a field of color, and also a field of string, and then the fish, which has no fields. So this is, yeah?
You don't want to have some way to restrict min fields so that it can only be on products, because otherwise you could end up with.
Yes, so I will go into that later. So the main problem with this is not really restricting that you really have like a choice and inside a product. So that's what the new version, this generics SOP, which comes from sum of product, allow. So it has the invariant that you really have a sum of products. So a choice of fields. But here, well, you don't really need this. This is a problem. But if you do everything sort of okay, so you only write non-stupid things, it works. And even it works if you write some stupid things. So.
Will you be going into labels for things, or are we just going to be sticking with this?
Yeah, we can go. This is like a conference thing. So if you want to know about how you can have like the fields for the names of the record fields, I'm okay to do this.
That would be really good, because I find that the labels are the things that always break everything. Like everything's always amazing in theory, but as soon as you throw labels in it,
I will.
Even the name of constructors are hard.
Yeah, they are now here. Yeah, that's right. So we're missing all the sort of metadata of the thing. So this is going to be enough to define like a quality because you don't care. But if you want to define like show, you need this information. I will show you how it's done. But it's right now. It's just let's keep it easy until here. So okay, now weird naming, because this is, doing this with these names would be just extremely easy for everybody. So instead of no fields, we are gonna call it.
Alejandro, before you move on, what's going on with the type variable?
Oh yeah, sorry. No, actually we don't need this. It would be, we can do it this way.
Okay.
So you can think like all of this has an A at the end also, but
Something?
Yeah, okay.
huh? I hope this compiles actually. So.
Yeah, I was just saying that you need to turn on the type operators.
Oh yeah. Oh. Okay. Public service announcement. You can write language in small letters, so you don't have to shout to me all the time.
I don't think I ever knew that.
Yeah, that's and color doesn't
That's really nice to know.
and color doesn't exist, so I will just have a stupid data type. So I just assume there is a color, so it doesn't really matter what color is here. But I needed to compile because I'm using it here in the field of color. So it is already compiles, which is okay. So we had a way to represent our data types with these things. So as I said, these names are not the real names, and that's maybe something which is a bit. So instead of no fields, people call this U1. And that's from unit, and the 1 is because it has one type variable. So, I mean, if you want to think this is a reason, that's. And then the field is called K1, takes an extra argument which is useless, and then the type an A. So this is actually defined like this. So that's U1 and K1 are the real names in GHC generics. So if you look at the documentation, this is what you will get.
K stands for what?
K stands for constant. So that's because if you think of this being a functor, this is a functor which is constantly T regardless of your choice of A. So that's like where the theory comes from. By the way, this idea of having like sum and times, it's also why these things are called algebraic data types, because they look like high school algebra. You have sum, products, and then numbers, which are the constants. Okay, so we had the first thing. We can now describe every data type, and well, not every data type, just simple algebraic data types. So actually, if you want to expand about your choice of data types, you need more power to do this. But people also have agreed that it's enough for this thing for the main uses. So you don't really want to do generic programming of weird data types. You want to do generic programming to remove your boilerplate on simple data types. So this is what people agreed after kind of 10 years of research, that okay, this is a good balance. So that's why it's built in. Okay, so this is great. So we have pets, and we can represent pets. So let me just copy it here. But I have no way to turn a pet into a representation of pet and the other way around. I need to do this because if I want to work over this thing, I first need to turn a pet into the representation of pet. So that's the second part of a generic library. You need to have a way to turn one thing into the other. So you need to. So you can have pet to representation, which would take a pet and turn it into a representation of pet of A. Again, this. And then, well, if you have a dog with a name, this is like, okay. So now we have to say which choice we take. So just to make things a bit more clear, this is supposed to have a parenthesis there. So because I don't want to go into infix operators and things like that. So the dog is the first thing. So you go 1 on the left, and then you are here in the field right. So you want to go 1 on the left. And then you need to give me a field of a string, which is just a field, which is the constructor of field. And then the string, which is the name. So this is how we turn the dog into the generic representation of a dog. So now we will do the fish, and then you will have to do the cat. So if we want to go to the fish, we have to go 1 on the right, and then we are into this big parenthesis, and then 1 on the right again until we get there. So 1 on the right and 1 on the right, and then we have no fields. So I hope this compiles. Yes, it does. So yeah, can you finish writing the cat part? Yeah. So yeah, have a color and a name again. Yeah. So we go 1 on the right, and then we are here. Then we have to go 1 on the left. And then we have a field, which is the color, and both a field, which is the color, and a field, which is the name. So I will try to compile it, and it works, which is great. So we now have a way to get from the pet to the generic representation, and you can sort of easily write the other way around. So you get the representation and turn it into a pet just by sort of reversing. So you just take this, put it there, and it's like quite easy. Well, so stupid that actually GHC does this for you. So you can ask to write this code for you. And I will show you how to do it. But before, let me introduce this sort of idea of generic conversion function in form of a type class, because, well, this is great. We can turn a pet into a representation of a pet. But what we really want to say is, OK, how do we turn any A into the representation of this A? So we want to have a type class, which is what makes this connection. And this is what it's called generic in GHC. So we say that something is generic, and then what kind of information we need to give. And this is where actually some of the fancy GHC features come handy. Because, well, a generic representation needs a type. So I need to tell you what is the representation of my type. So I need to give you some type, which is the representation of this type A. This is going to be a functor of this form, always something of this form. We cannot guarantee that actually it's on this form, but it will break later if it's not. And then we need a way to turn, like, I always forget, one is called to and one is called from, and I always forget but essentially, this takes an A and turns it into the, let me first. Sorry, let me call it T. Just so it.
Is this supposed to be a class, no?
Yeah, this is. Sorry. That's class.
Doing gadgets for too long.
Yeah. So we have a way to turn this T into the representation of T, and remember, because this is all a functor, we need this extra A, and the other way around. So that's. That should be good enough. So we can. So if now you have an instance of generic, you have to give the representation and the conversion function from one way to the other. And I guess I need to. That was too long before I need to add yet another one. So yeah. So really like the instance of generic for a fish, not for a pet. So the representation of a pet is this type we defined before. You can copy it or you can reuse it, and then 2 is going to be pet to representation, and from is error exercise to the reader. And hopefully all of this keeps compiling. Oh dear. I need to say that this is a functor, so I need to give a kind signature. Yeah. So this. Okay. Who is familiar with kinds? Okay, then you know what this means. So that's good. We need to give it a type constructor, so it has to be something from star to star, and it seems that it's not able to infer this from the fact that we use it this way. So, yeah.
Real quick, where's color, data color?
Oh, it's just defined on top. It's just like I assume there is something.
You data
like,
color and you don't use it.
Yeah. Yeah, we need to have type families to have this type family on the type class. So now we're using type operators because of this and this.
This type family provides kind signatures.
Maybe I'm not really sure.
You don't need to add it.
No?
No, it works. So I've just compiled it. So my usual way to do these things is I do it, and then usually GHC knows which flags I have to do, which always I find this quite weird. Like, okay, you tell me I have to have this flag, so why don't you just like go on? Okay, so as you can see, well, we have all the blocks to define like what's the representation, and we have this idea of converting from one to the other, and this is always very boilerplatey. So you have to go some amount of times on the left, and then one time on the right, so you get to the right constructor, and then you have a product of a lot of fields. So this is, as I said, this is boring. I forgot to mention this is actually, so the types are checked. So if I actually sort of say, oh, I just want to have a 1 here. Not a 1, because then it will tell you something about num. It will break, because I was expecting a field of type color, and you gave me a field of type bool. So I think this is something really nice which sets this apart from like reflection and things like that. Every type is checked. Even though we are working generically, everything still has to work. Everything has to like go well with each other. So let me just F(C). So of course, I mean, writing all of this is quite boring. So what we can do is to ask GHC to write this for us. So let me open yet another one. So I know I will need this, and I know I will need this. So module generics 3 where, and then I will just copy my pets. It's here. And yeah, and then I would say deriving generic. So it's going to write generic for me. And let me just introduce the color, because now I really need to do something. So let's just say a color is a 3 ints representing an RGB. So you can. So hopefully, if now I load it, oh yeah, I need to bring this into scope. So this is in the module ghc.generics.
How does the deriving of generic work? Is that baked into the
It's built into the compiler. Yeah, that's the only bad. Most other libraries have like template Haskell to generate this for you. So because there is, but I mean, built into the compiler and template Haskell are like the same scene. So I mean, just one is like, oh well, this is a scene, but we like it so much that we put it into the compiler. But
Is there a summary document of all the different ways that deriving works? Because coming from Scala.
Yeah, there is like a, if you go to the GHC users manual, well, you have the Haskell repo, which tells you like for the Haskell standard libraries how this works, and then there is thing which is called extensions to the deriving mechanism, and they say what is all the extensions, so you can derive functor traversable, all of that. So okay, let me do this, and then I will answer. Somebody was asking about the metadata. Oh, was you? Yeah. So if we ask the kind of what is the representation of a color, let's keep it. I'm sorry, it's called rep. I always forget this kind of things. Okay, so it's so this kind bang tells me tell me what's the result of sort of evaluating this type family. So wow, that's a lot of things. So you can see that at some point, let me make it bigger because, so that's only for color, which has like one constructor and 3 fields, and you will see that there is some and there, and then you will see that there is this rec0. Rec0 is just a synonym for K1R. So that's, but you can see there is like the 3 ints there, and there is all this metadata that you wanted to have. So it's like this metadata tells me that this is the color defined in the module generic 3 in some package called main, and there is a constructor C1 which has a list. So that's like a cons of metadata. So you tell me that this is like it's called RGB and it's prefix, so it's not an infix operator. And I forgot what false means. And then there is for each of the fields, you tell me, well, this is just a field, and there is a bunch of nothing because it's like a regular field, so it's not unpacked, there is not a strict, it is lazy. So it's really a lot of information put into the metadata. So if we ask for the kind of rep of pet, that's gonna be like, oh, it's not as big. Oh, great. But again, you see like all this metadata, and there is all these extra things, and all. So if we want to put metadata in our original framework, we can do it sort of easily, because metadata is something which exists only at compile time. It doesn't exist at runtime. So we can just say that, adding some metadata m to some constructor or thing A is just like having this C of A, because this m is just going to be used at compile time. So you are really forgetting information on the runtime. It doesn't matter. So we don't keep like flags at runtime. This is all on the type level, which I think is also kind of nice. You can use this metadata, but only at compile time. Once, then you have to forget about it. So, you already built your own sort of generics library, except for the fact that, well, it doesn't include too much metadata, and this you have to write this yourself. But apart from that, that's all the pieces you need. So any question up to this point? So the next step is going to be like, okay, assume we have this weird thing. How do we define generic equality, for example? How do we define a generic operation? But you really need to understand all these small pieces. So any question? No? I will take it. Yeah.
What's the R and the K1 again?
Oh, yeah. So this is actually something which they thought, and it was removed. So imagine you have a list of A, or a list of int. You want somehow to differentiate at the type level whether the thing you have is a constant, which comes like just a normal thing, like an int which appeared there, or an A, so it's a type variable which appears there, which just happened to be an int because it was, and then you have K1P, P being for parameter, or if it's a recursive appearance of the type itself, like in list you have A and list of A, so then you have Q1R for recursion. It turned out that this thing is not really useful at all, so the differentiating between these things is not useful. unless you go into like generic for type constructors. If you want to define like, there is a type class called generic one, which is for things with a type constructor, and then it becomes helpful because you want to distinguish these things. So at the end, it always uses rec0. So that's like, rec0 is like the K1R. It doesn't really matter, just like the constant thing. And here you can, by the way, you can also see this U1 because fizz has no field. So you have.
And so then if we were defining like a parameterized type, like pet of A, and it potentially has some recursive constructor, then the R would.
But there is also the question whether you want to define generic for pet, or generic 1 for pet, or generic for pet of A, regardless of the A. And usually the second is more useful. So you always want to see to everything as ground types, not.
Can you show the instance rows there again?
The instance for?
Yeah.
Yeah. So.
Yeah, I gotta parse here on the instance type.
Yeah, I don't know how this. You are missing the where. Good. So now we have to define our generic things, and this again yet another trick you have to play. So we are going to define generic equality. That's like the simple thing you can think of, because the idea is, well, if you have two fields, and these two fields implement EQ, then you just call recursively like the equals. If you have a product, you have to check that both things on a product are equal. So that's like checking a tuple. And if you have one of these sum, you need to know that they both go into the same path. So they both go to the left, or they both go to the right. And if they do, then keep looking for equality. And otherwise, just you say they are not equal. So you return a false. And then every U1 is equal to every U1, because, I mean, there is the only thing it can be. And of course, I'm not talking about laziness or anything like that. So you can define how two U1s are equal in a ton of ways, but let's do it easily. So the trick we are going to play here is we are going always to define a type class for every generic operation we want to have. So let me call generic equality. And this generic equality will take a parameter which will be like the representation of your data type. So let me maybe call it R. So this generic equality operates on the representation of these building blocks. And then what you have to tell me, because that's equality, so you give me two R's of A, because remember they are always functors, so we always have to do this, and then you give me a bool. So that's the same equals you would define, just you use representations instead of like your real things. And then I will do it at the end, but at the end, the real equality will be just like use this operation to turn your data type into the generic representation, then use this equals on the generic representation, and then you just, in this case, you get a bool. But if you get something on the generic representation, again, maybe you need to turn it back. So imagine you have, I don't know, breed two pets, and then you get a new pet. So then you have to turn the pet back from representation of pet into pet. That was a terrible example. But so as I say, we need to define these equals for every possibility here. So let's define one simple one and one complicated one, and then you can define the rest. So remember, we have 4 cases: sum, product, a field, or an empty list of fields. So if it's an empty list of fields, then equals U1, U1 is true. This can only be U1. So these two things are equal. Then you may have a field. So remember, this was rec0 of t. So by the way, I forgot what is the. So rec0 is k1 r, and I forgot what is the name of the constructor. So k1, it's here. There should be a.
Probably on line 15 you want where class rather than data.
Huh?
On line 15
Oh, sorry again. That's somehow it thought that I'm just defining. Yeah, and here I always forget, but like the K1 is the constructor's name K1. I always forget about these things, so sorry about that. So so if I have two of these fields, I will have a value for the first field and a value for the second field. So when do I say that these things are equal? So I don't know what the t is. So I really need to have that this t somehow also implements equality. So if t implements equality, then I can just check this thing. And hopefully this, I need type synonym instances. Q. I don't want to enable more things. So that rec0 is like K1 of R. And so just define it for every K1 of R. So you will see here also a pattern which repeats very often is that if you try to implement generic equality, you get to the fields, and then these fields have to implement equality again. So you end up always having this thing which in the fields you have a call to the original equality, and then problem. So this happens very often. So you are defining show, and then you can only generically show something if each of the fields have the show, which maybe the field is again yourself. So it goes back to like your operation and converts a bit more of it, and then it calls a generic representation. You can think if you have something like a list, it's not turned completely up down into generic representation. It just goes one level down because there's only one level, and then if it needs to inspect the tail of the list, then it will go one level down into the generic representation and so on until you are done. Yeah.
Is there a reason we're not like the constraint is equality t instead of g equality t? So is there a reason why like the x and y?
Yeah, because this t doesn't represent. It's not a representation itself. It's just the name of a type.
It's just
Yeah. So you can, for example, see this also on the kinds. We couldn't do this because the t is of kind star, and g equality works on star to star because it's representation. So that's also like a more technical reason why you have to do this.
And it's also because like we only went one level down.
Yes, that's.
It was like all the way down.
Yeah, there is also one library called regular. Is essentially taking this idea to its consequences. So what if instead of doing it one level, we go full level down, and then of course you don't need this EQ thing because you just define equality over everything down. But that's like I say, it's not the winning approach. So I'm just assuming that there are some disadvantages. I haven't worked with regular, so I don't really know what are the practical disadvantages. But so okay. So then we need to do the tuple thing. So we want to define equality on F and G. Okay. So what can we do here? Okay. So these things have this form. So the constructor is called star2. So if we want to define this thing, we have sort of the same problem as with the field. We can only do this if it happens to be the case that both f and g implement the generic equality. But now it's actually the generic equality because these f and g are representations themselves, not field, not just types. So we really need like equality on f and g, equality on g, and then that means that these things are equal if equals xy and equals x prime, y prime. So hopefully all of this works. Type operators. Well, and so maybe you can try to define the missing case. So the OR case, and to give you a clue about what you need for this, let me get you the info of OR. And then you can see that instead of one on the left and one on the right, it's defined here. So it's called L1 from left and R1 from right. So remember, the idea here will be if both go into the same direction, then you can keep looking. If they go into opposite directions, then we know they are not equal because they represent different constructors. So good thing is we are so close.